Hello there. In this video, we're going to derive the process on how to construct a confidence interval for the population proportion, where a population proportion pretty much describes the percentage of people that satisfy some criteria that you are interested in. But before we get into that, we're going to recall a concept from a long time ago that is going to be used in this derivation. And that property is this. So recall, let x be a binomial random variable. So if you don't remember what a binomial random variable is, it's a random variable that has the following distribution: ncx, the number of combinations, times 1 minus p to the m minus x times p to the x. Here, n is the number of independent trials, and p is the probability of success of getting what you want. So the important property that we're going to use here is the following. But before we get into that, let's also recall another property. So also recall that the expected value of x is going to be equal to n times p. And also the variance of a binomial random variable is going to be np1 minus p. And we've talked about these properties in the past, of course. But if you don't remember, you can just take them as assumptions for now. So, if n is large, and you can sort of, mandate what you think is large or not. Some people use some requirements, like n is bigger than 30, or n is bigger than 50, or like n times the percentage is bigger than 10, or something like that. But it really depends on a lot of things. Then, the normal distribution can be used to approximate a binomial random variable with mean and variance given above. And this is really important, and we're going to take advantage of it. So recall this. So recall all probabilities for the following random variable, z is equal to x minus mu divided by sigma, follows normal distribution. I'm going to put mu x and sigma x here. So of course, if n is large, then we can replace x with a binomial random variable, since they're going to be approximately equal to. So if that is true, well, mu x is the same thing as writing the expected value of x, which is equal to mp. And also, sigma squared x, which is the same thing as writing variance of x, is mp1 minus p. So from these two things, we can find that mu x is equal to mp, and sigma x is equal to the square root of mp1 minus p. So that means what? So that means this variable z is approximately equal to x minus np divided by the square root of np1 minus p. And this is approximately equal to a normal distribution. Okay, great. So why do we really want to consider this? Well, p pretty much represents the probability of something occurring, which is a percentage in some way. So this percentage is also related to the percentage of people, that satisfy some criteria. Because if it satisfies some criteria, then that's pretty much like a success in our eyes. So this probability p is going to be associated to a proportion in some way. So pretty much what we're going for here is we're trying to construct some confidence interval for this proportion of the population. So since we've pretty much associated this approximation to a normal distribution here, that means we can use a z-score, namely negative z alpha over 2 and z alpha over 2, for the confidence interval for the population proportion. So these are going to be our critical values for a population proportion confidence interval. So that actually saves some, some headache, because you don't have to use like a t distribution or a chi-square distribution or something else like that. So since normal is not a stranger to us, that at least gives us some simplicity. So since we're going to construct a confidence interval, we're going to let C be equal to the middle region. With that being said, that means this is going to be a two-sided test. And remember, when I say a two-sided test, we're going to be looking at the null hypothesis that the population proportion is equal to something, and the alternative is going to be pi does not equal to whatever percentage that they said. So that's what I mean by two-sided. All right, so according to this picture, the probability that z lies in between minus z alpha over 2 and z alpha over 2 is going to be equal to c, and that's coming from this picture. So there's lots of random variables that are associated with z, so we're going to choose this approximation. So if that is true, then the probability that minus z over 2 alpha over 2 is less than or equal to x minus mp over the square root of mp1 minus p is less than or equal to positive z alpha over 2 is approximately equal to c. Not exactly, but approximately equal to, as long as n is large. Keep that in mind. All right, so I'm going to do some algebra here, so I'm going to rearrange this. I'm going to multiply both sides by the square root. So that's going to give me the probability that minus z alpha over 2 times the square root of mp1 minus p less than or equal to x minus mp less than or equal to z alpha over 2 times the square root mp1 minus p, and this is going to be approximately equal to c. So remember what we're pretty much going for here. We're trying to get this probability p by itself, since that's the closest thing we can get to a population proportion here. All right, so that means I'm going to get rid of x first. So I'm going to subtract x from both sides. So that's going to give me p minus x minus z alpha over 2 square root mp1 minus p less than or equal to minus np less than or equal to minus x plus z alpha over 2 square root mp1 minus p, and this is approximately equal to c. From here, we're going to divide both sides by minus n. So keep in mind I'm dividing by a negative number, so I'm going to flip my inequality signs around. So this is going to give me the probability. So negative negative is a positive, x over n. Negative negative is a positive again, so that's going to be plus z alpha over 2 times the square root of mp1 minus p all over n. That's going to be greater than or equal to p greater than or equal to negative over negative is a positive, x over n. Positive divided by negative is a negative, z over alpha over 2 times the square root np1 minus p divided by n, and that's going to be approximately equal to c. Same approximation. I'm going to write this from least to greatest because this looks a little bit awkward with the greater signs facing the left-hand side. So that's going to be the probability that x over n minus z alpha over 2 times the square root of mp1 minus p all over n less than or equal to p less than or equal to x over n plus z alpha over 2 times the square root of np1 minus p all over n, and this is approximately equal to c. All right, another quick thing. We're going to sort of simplify this. So recall, what is the square root of n divided by n equal to? So we can rewrite the bottom as square root of n times the square root of n, since that's going to be half n plus a half n, that's going to be a whole n. So those are going to cancel, so we're just going to be left with the square root of n on the bottom in each of these cases. So that's going to give us some rearrangement that will be useful. So we can write this as the probability that x over n minus z alpha over 2 times the square root of p1 minus p over n less than or equal to p less than or equal to x over n plus z alpha over 2 square root p1 minus p over n, and this is going to be approximately equal to c. All right, so from here, where do we go here? So what do we have? So we have p in the middle of this expression. So that's a good thing. But there is a subtle issue here because we also have p here, p here, p here, and p here. So we have p on both sides. And also we have this expression here, x over n. So what exactly is x over n? Well, x is pretty much going to be the number of successes, right? Or the interested number of successes, and n is going to be the number of trials. So pretty much what this is going to be a sample proportion. So this is going to be a sample proportion. And I'm going to note that by p hat. So p hat is going to represent my population, my sample proportion. So once I rewrite that, what do I get? So that's going to be the probability that the sample proportion minus z alpha over 2 times the square root of p1 minus p over n equal to p less than or equal to my sample proportion, p hat, plus z alpha over 2 times the square root p1 minus p over n, and this is going to be approximately equal to c. All right, so this gives us something a little bit more useful. So the sample proportion is the proportion of people in your sample that satisfy your criteria. So that's pretty much the middle of this confidence interval. And what we can do with this p, 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 and p, we can use p hat as an approximation for p. Which is a fair thing, right? You know, the sample proportion is an estimate for the population proportion. So this approximation here is going to actually sort of compile into like a double approximation, because the approximation came from the binomial distribution, and now we're using another approximation to sort of get this confidence interval. So you see where a lot of assumptions actually are really important in this process. So what do we get here? So the probability that p hat minus z alpha over 2 times the square root of p hat all over n is less than or equal to, and now I'm going to redefine this middle thing as pi, because usually we use Greek letters to represent the population parameters. And that's going to be less than or equal to p hat plus z alpha over 2 times the square root of p hat 1 minus p hat over n, and this is going to be pretty approximate equal to c. Maybe really off, maybe really close, we don't know. So just some observations here. Notice that this and this value are the same. So I'm going to define this as the marginal error for my population proportion confidence interval. So what do we get here? So the probability that our sample proportion minus our marginal error less than or equal to pi, less than or equal to the sample proportion plus our marginal error for the confidence interval is approximately equal to c. So this is our confidence interval. So I'm just going to rewrite this in the more traditional way that's maybe a little bit more familiar to you. So the c% confidence interval for the population proportion pi is equal to the sample proportion minus the marginal error, comma, the sample proportion plus the marginal error, where the marginal error for pi is going to be equal to the z critical value times the square root of the proportion of successes times the proportion of successes divided by the sample size. And this is the confidence interval for the population proportion pi. And keep in mind, this is a two-sided interval, so you're going to be associating this with the null hypothesis that pi is equal to something, with the two-sided alternative that pi does not equal to something. And keep in mind, all these calculations are based solely upon the fact that n must be large, and some people require that np hat be greater than or equal to 10, and np hat also greater than 10. Some people impose more restrictions, but nonetheless, n has to be sufficiently large. So this is pretty much how you construct a confidence interval for the population proportion, and in the next video I'll pretty much work through an example to sort of show you how all of this works together and how to use it for a hypothesis test.